Good morning, students. Today's topic is magnetic circuits. So generally, the electrical network analysis is broadly divided into two categories. One is circuit theory, another one is magnetic theory. Circuit theory, you are going for the electrical circuit analysis, while you are coming to the magnetic theory, you are going for the magnetic circuit analysis. So in this magnetic circuit analysis, we are main concentrated on the inductance. It may be a self, it may be a mutual. So with respect to these two things, we are going for the analyzation of the magnetically coupled circuits. The prerequisites of your magnetically circuit analysis is basic fundamentals of mathematics. So that is integration, differentiation, and etc. And also the engineering physics. So in the engineering physics, you studied different laws also. Ampere's law, thumb rule, Fleming's left hand rule, right hand rule, Faraday's laws. So all these are the prerequisites of this subject only. In previous semester, you studied the basic electrical engineering. So that is also one of the prerequisite. There you studied different passive and active elements. So here also you are using the same elements. Okay. The subtopics of magnetic circuits as per the syllabus of JNTUH is self-inductance and mutual inductance, coupled circuits, coefficient of coupling, dot conversion, ideal transformer, equivalent T for magnetically coupled circuits, and impedance transformation. So once you know the concept of impedance and reactance, so how the impedance is transformed for the magnetic circuits, all these studies you are carrying in this unit. Okay. So now coming to the introduction. So coupled circuit. So coupled circuit means minimum two coils must be there. So if you are giving excitation to the one coil, there is a induced EMF generated in the another coil. They are not electrically coupled. They are only magnetically coupled due to the magnetic flux produced by the first coil links with the secondary coil and induced EMF is generated. So the coil must be considered in such a way that so it must be having less resistance, so almost it is negligible resistance and more inductance. Okay, so such type of coupled coils you can be represented in electrical circuits. So that is, you can call it as a conductively coupled circuits by using the basic equations such as KVL or KCL. Okay, so now we are going for the EMFs induced in a particular coils. So the electromagnetic induced EMFs are divided into two categories. One is statically induced EMFs, another one is dynamically induced EMFs. So what is a statically induced EMF? So the name itself says that it is a static. The device must be a static. So then those devices, if you are getting any induced EMFs, then you can say that those induced EMFs are statically induced EMFs. So these are again subcategorized into self-induced EMFs and mutually induced EMFs. So what is a self-induced EMF? So self-induced EMF means if you take a single coil is excited by some voltage, a current will flow through the coil. So once the current is flowing in the coil, according to the thumb rule, around the coil there must be an induced EMF generated. So that is around the coil, uh, around the coil. So there must be a magnetic flux generated. So once the magnetic flux is generated and the coil having certain turns, so the induced EMF can be calculated with respect to the number of turns of the coil and the rate of change of flux. The rate of change of flux. So that induced EMF, you can call it as a self-induced EMF. So let us assume two or more coils are there. So one of the coil is excited, the current will flow through the coil. Once the current is flowing through the coil, so almost the magnetic field around the conductor will be there. So this magnetic field cuts the other coils. This magnetic field cuts the other coils. Ultimately, there is a induced EMF generated in the other coils with respect to Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. So this type of induced EMFs, you can call it as mutually induced EMFs. Mutually induced EMFs. So that means the mutual between the one or more coils. Then coming to the dynamically induced EMF. So name itself dynamically, it never be a constant. It never be a constant. So it will be changes with respect to time. So whenever a conductor is uniformly rotated in a magnetic field, whenever a conductor is uniformly rotated in a magnetic field, so the conductor is rotating in a magnetic field, the magnetic field moves from north pole to south pole and south pole to north pole. So it cuts the rotating conductor. So due to that, an induced EMF is generated. So if it is uniformly rotated conductor is there, the waveform will generate a sine wave. It generates a sine wave. So if it is a non-uniform, so it will generate a wave or a periodic function. It should not be a linear, it may be non-linear. So such type of induced EMFs, you can call it as a dynamically induced EMFs. Next, coming to the statically induced EMFs. So already you discussed the statically induced EMFs are one is a self-inductance, another one is a mutual inductance. So for a magnetically coupled coils, you have to go for the self-inductance of the coil and mutual inductance of the coil. So for understanding this, the best example is a transformer. So transformer is a static device. Transformer is a static device. We are giving excitation in the primary side and you are getting induced EMFs in the secondary side, and the bulk amount of power is transferred from one side to another side without change in frequency. So this is due to the mutual induction between the two coils. So according to Faraday's laws of electromagnetic induction. According to Faraday's laws of electromagnetic induction. Are you understanding? So now coming to the example, so I have taken a coil. So the number of turns of the coil, let us assume n number of turns are there. N number of turns are there. So the coil is excited by a current of I of t. Once the current is flowing in the circuit around the coil, it will develop the magnetic field. So let us assume the flux produced by the coil is phi. So the voltage drop across the coil, is V volts. Then Faraday's laws of electromagnetic induction will give the induced EMF generated by the coil. V is equal to N into d phi by dt. N into d phi by dt. So the above equation I am multiplying and dividing by di. I am multiplying and dividing by di for d phi by dt. So d phi by dt is equal to d phi by di into di by dt. So now I am substituting this equation in above. Then what you can get, v is equal to n into d phi by di into di by dt. So now this expression, so that is n into d phi by di, I am represented as L. I am represented as L. Then the induced EMF V is equal to L di by dt. So whatever the induced EMF generated in this circuit is a voltage drop across the inductor only. Is the voltage drop across inductor only. And the L value, so what is L? L is n d phi by dt. N is d phi by di. So the L is a self-inductance of the coil. L is a self-inductance of the coil, and the units of inductance is henries. The units of inductance is henries. Now coming to the another example, mutual induction between the coils will get a mutual inductance. Okay, so let us assume two conductors are there. So this is one conductor, this is another conductor, or two coils are there. So coil 1 and coil 2, they are very nearer each other. So if a current is carrying in the first coil, if a current is carrying in the first coil, so around the coil the magnetic flux will be produced. So this magnetic flux, whatever produced by the first coil, it cuts the second coil. So there must be a induced EMF developed in the second coil. Okay, so here I have taken a pictorial diagram with respect to the equivalent circuit. So here two coils are there. So one is having a turns of N1 and second coil is having a turns of N2. So the self-inductance of first coil is L1, the self-inductance of second coil is L2. So now I am excited a current of I of t in the first coil. So due to that, an induced EMF is generated in the first coil, and also due to the flux produced by the first coil, it cuts the second coil, and induced EMF is generated in the second coil, that is V2. That is V2. So which flux is cut? So the flux cut by the coil is phi 12. Phi 12. And phi 11 is the flux produced by the first coil. The flux produced by the first coil. Okay. So with respect to this, I am writing the KVL equation as total flux is equal to, so total flux phi 1 is equal to phi 11 plus phi 12. So self flux is 11, and the flux linkage between coil 1 and coil 2 is phi 12. So now the total flux produced by the first coil is phi 11 plus phi 12. So now V1 is equal to voltage drop across the first coil, V1 is equal to N1 d phi 11 by d I1 into d I1 by dt. So now, so this value, so n into d phi by di can be represented as inductance. So that value I am taking as L1 di1 by dt, where L1 is the self-inductance of the first coil. So now coming to the second equation, an induced EMF is generated in the secondary, so that is V2. So V2 is equal to the secondary coil number of turns is how much? N2, and due to which flux it is developing phi 12. So d phi 12 divided by what is the current flowing in the first coil? I1. So di1 into di1 by dt. So now this value N2 into D512 by Di. I am representing as M21, M21. So into Di1 by Dt. So here the induced EMF is developed due to mutuality between the two coils. So the mutual inductance is represented by M21. So it is a second coil. See, it is a second coil with respect to first current. So M21. So 2 referred for you are measuring the voltage at the secondary side. So due to mutual inductance, so second mutual inductance with respect to first current. With respect to first current. Okay, are you understanding? Then coming to the second case. So here I am taking the same circuit, but I have excited in the secondary side with a current of I2 amperes. So here L1 is the first coil, self-inductance, L2 is the second coil, self-inductance, N1 is the first coil, number of turns, N2 is the second coil, number of turns. So once the excitation is given to the second coil, the current I2 will flow through the circuit because of closedness. Due to that, the two fluxes will be produced. So one flux is purely for second coil, so that is 522, and another flux links with the first coil, so that is 521. That is 521. So due to this 521, the first coil will induce an voltage of V1. So now the overall flux phi2 can be represented as phi21 plus phi22. Then coming to the KVL equations, the first voltage V2 at the secondary side is equal to the number of turns of the secondary coil is N2 d phi22 by di2 into di2 by dt. So 522, due to that flux only the induced EMF is generated in the secondary side. So now the N2 d 522 by di2 you can be taken as a self inductance of the secondary coil L2. So V2 is equal to L2 di2 by dt. Then coming to the calculation of V1. So how we are calculating the V1? V1 is getting with respect to 521 flux. V1 is getting with respect to 521 flux. Okay. So V1 is equal to the number of turns of the first coil N1 into d521 divided by di2 into di2 divided by dt. So now this term N1 d521 divided by di2 I am taking as M12. I am taking as M12 into di2 by dt. So M12. So one is you are measuring the voltage at the first side. So coil one side. So that's why the mutual inductance will be started with 1, and due to which current? I2 current. You don't have any I1 current in this circuit. So only I2 current is there. So that's why M12. So this is the mutually induced EMFs with respect to mutual inductance. Okay. So now the two circuits, so case 1 and case 2, two circuits are taken. If the two currents I1 and I2 both are same, then the mutual induced EMFs with respect to mutual inductance M21 and M12 must be same. And this is also due to mutuality of the two coils. So it is also measured with Henrys only. So the units of mutual inductance is also Henrys. Are you understanding? Now coming to the relationship between mutual inductance and self-inductance of two coils. So here I have taken a two coils. So the number of turns of first coil is N1, the number of turns of second coil is N2. The primary side voltage is V1 with a current of I1. The secondary side voltage is V2 with a current of I2. So due to the first current, the flux produced is Phi12. Due to the second current, the flux produced is Phi21. So now the self fluxes are Phi11 and Phi22. Phi11 and Phi22. Okay. So here, so listen once again. So we are concentrated with respect to the self values of two coils and also mutual induction between the two coils. So already you know that L is N into d phi by di. So here I am taking L1 for the first coil, N1 phi1 by I1. For the second coil L2, I can represent as N2 phi2 by I2. The mutual inductance M21. The mutual inductance M21. So M21 means secondary mutual value we are represented with respect to first current. With respect to first current. So that's why N2 phi1 by I1. So M12. So M12 means, so M12. So 1 means you are considering the mutual inductance with respect to first coil, with respect to first coil due to second current, due to second current. So N1 phi2 by I2. So now I am multiplying the two equations 1 and 2. So M12 into M21 is equal to, so N1 phi1 by I2 into N2 phi1 by I1. So if you simplify, you can get N1 phi1 by I1 into N2 phi2 by I2. So what is this value? N1 phi1 by I1 is L1, N2 phi2 by I2 is L2. So that is M12 into M21 is equal to L1, L2. So if you assume the both currents are constant with the same values, then M12 must be equal to M21. So if M12 must be equal to M21, let us assume M. So M is the mutual inductance. So M square is equal to L1 L2, or M is equal to root of L1 L2. So there is no leakage currents. It is a ideal condition. Under this ideal condition, the mutual values with respect to first side or with respect to second side must be same. M12 must be equal to M21. So that is equal to M. So M must be under this condition is root of L1 L2. Now coming to the coefficient of coupling. Coefficient of coupling. So coefficient of coupling is most important for all transformers or any mutually coupled circuits, because it will give the degree of coupling. It will give the degree of coupling. So generally the K value must be represented with respect to root of phi21 into phi12 divided by phi1 into phi2. So the phi21 and phi12 are the fluxes produced from secondary to primary or primary to secondary. So phi1 and phi2 are the fluxes purely related with the first coil total flux and second coil total flux. So the K value, so it is the coupling coefficient, it is the coupling coefficient or coefficient of coupling. So the K value must be root of 521 into 512 divided by 51 into 52. So now L1, so L1 is N1 into 51 by I1. So M12 is N1 512 by I2. L2 is N2 52 by I2 and M21 is N2 521 by I1. So now I am taking the first value is 521 by I1. So here you can get the 521 value. Here you can get the 51 value. So that is M21 I1 by N2 into N1 by L1 I1. So that is equal to, here the numerator and denominator I is there, gets cancelled. So finally you can get M21 by L1 into N1 by N2. Then I am going for the second value. So that is 512 by 52. So 512 you can get from this expression and 52 will get from this expression. So M12 I2 by N1 into N2 divided by L2 I2. So here I2 is common, gets cancelled. So finally you can get M12 by L2 into N2 by N1. So now the coefficient of coupling is, under the radical you have to substitute 521 by 51 multiplied by 512 by 52. So if you substitute the above values, M21 by L1 into N1 by N2 into M12 by L2 into N2 by N1. So here N1 gets cancelled, N2 gets cancelled. So finally you can get under the radical M21 into M12 divided by L1 into L2. So if it is a best coupling, there is no leakage flux. If there is no leakage flux, M21 value must be equal to M12. So you can write it as M square divided by L1 L2 under the radical, or you can write M divided by root of L1 L2. So now the M value is root of L1 L2 for a best coupling. So already you are studied in the previous derivation. So from that, if you substitute the value of M is equal to root of L1 L2, so finally you can get the value of K must be equal to 1. The value of K is equal to 1 means it is a best coupling. No leakage flux. Total flux produced by the primary circuit, excited from the primary circuit, is purely linked with the secondary circuit. For inducing a voltage in the secondary side. Okay. So the range of values of K must be 0 less than or equal to K less than or equal to 1. So if K is 0, it is no connection between the coils with respect to distance. Okay. So already you know that the magnetically coupled coils means they are not directly linked. So it must be nearer distances. Then due to the one coil, there is an induced EMF in the secondary coil. So if the distance between the coils is very large, then you can say that there is no coupling. So at that time the value of K must be equal to 0. And for a best coupling or a perfectly coupling, the value of K must be equal to 1. So if K is less than 0.5, so it is loosely coupling. So that means not very nearer. So it may be certain distance. So and the value of K ranges up to less than 0.5 must be loosely coupling. and the value which is greater than 0.5 to 1, which is greater than 0.5 to 1, it ranges with tightly coupled circuits. Tightly coupled circuits. Okay, are you understanding? So here the most important things is mutual inductance. It measures with respect to Henry's, and the mutual inductance you are getting with respect to the Faraday's laws of electromagnetic mutuality between the two coils, and the self-inductance of the two coils and mutual inductance between the two coils can be represented as, for a best coupling condition, M is equal to root of L1 L2, and the degree of coupling K must be represented as M divided by root of L1 L2. So if it is a best coupling, the M is substituted for root of L1 L2, then the value of K must be equal to 1. So most of the practical transformers also, you are going for the value of K must be very nearer to 1. So you are getting almost all manufacturing companies, you are getting most of the cases the coupling value must be 1. They are very tightly coupled, and we are getting the best transferring of power from one point to another point. So if any design properties are changes, then ultimately the value of K must be reduces. Are you understanding? Now come to the last induced EMF is dynamically induced EMF. So I already told, let us assume a conductor is rotating in a two magnetic fields, it induces an EMF. So the induced EMF can be represented as flux cut by the coil with respect to time. So that is rate of change of flux. That is rate of change of flux. So mathematically you can write it as B into L into dx by dt, where B is the flux density, L is the length of the conductor, and dx by dt is the change of displacement, rate of change of displacement. So you can call it as velocity of the conductor as V, So E is equal to B into L into V. So if it is the angle of rotation with respect to theta is there, then you have to consider the equation as E is equal to B into L into V sin theta. B into L into V into sin theta. So angle of motion is there. At that time you have to go for this equation. If angle of motion is not there, then you can go for the above equation, B into L into V. Are you understanding? So these are the induced EMFs with respect to those derivations. So now come to the dot conversion. So dot conversion is a very important concept. So this concept will give the induced EMF produced by the coils must be either in positive or in negative, will decided by the dot conversion only. So that means the polarity of mutually induced EMFs is taken with respect to dot conversion. Okay, so whenever two coils are magnetically coupled, if one circuit is excited, so the current will flow through the first circuit and induced EMF is generated in the second circuit. The current flowing through the first coil, so you have to take it as a dot at the starting terminal of the coil, and you have to measure the voltage. You have to measure the voltage. So that voltage must be a positive. So entering current with respect to dot is there. The induced EMF generated in the secondary coil must be a positive voltage. Otherwise you can call it as negative voltage. So that means the current is flowing for the leaving dot of the first coil. The induced EMF is generated. The polarity of that induced EMF must be considered as negative. negative. So to understand this, we are going for the simple pictorial diagrams. So the main concept of dot rules will be in such a way that if both dots are at the top and both currents are entering, so that is starting dots, then that mutual inductance is a positive mutual inductance. The dots, one is a entering current, one is a leaving current, then the mutual inductance must be a negative sign. So to understand this, let us take the first example. So here I1 current is flowing with a starting dot, I2 current is also flowing with a starting dot. So I am writing the KVL equations for the first side and second side. So the first side is, we are having V1 is equal to one coil L1, what current? I1 current, dI1 by dt, plus mutual inductance is M into which current? I2 current, dI2 by dt. So while writing in the second equation, so V2 is equal to L2 into dI2 by dt. So because L2 is carrying a current of I2 only. So the mutual inductance you have to consider with respect to I1 current. So dI1 by dt, M into dI1 by dt. So now this is the equivalent circuit I have represented for the first one. So coming to the second one. So figure C. So if you take the figure C, so I1 current is entering towards the dot, but I2 current is leaving towards the dot. So that means this mutual inductance is negative. This mutual inductance is negative. So that's why the first equations L1 di1 by dt must be same, but the next value is minus M di2 by dt. Similarly for V2 also, L2 di2 by dt is common, but the mutual inductance is opposing, so we are writing as minus M di1 by dt. So the equivalent circuit for figure C will be D. So similarly, if you go for the figure E, so for this figure E also, I1 current is entering towards ending dot and I2 current is entering towards starting dot. So that mutual inductance must be negative, same as the previous case. So V1 is equal to L1 di1 by dt minus M1 di2 by dt. So similarly V2 is equal to L2 di2 by dt minus M di1 by dt. So for figure E, so this is your equivalent circuit. And similarly for figure G, so here I1 current is having ending dot, I2 current is also having ending dot. So it is the first case. It is the first case is same as the last figure. So V1 is equal to L1 di1 by dt plus M di2 by dt. Similarly V2 L2 di2 by dt plus M di1 by dt. Are you understanding this? So whenever the current is flowing, both the dots are at the entering side or at the leaving side, the mutual inductance must be positive. So if one dot of one current is entering and another dot for another current is leaving, that mutual inductance is negative. Are you understanding? Okay. So now coming to the application of dot conversion. So here, due to the current, the induced EMF is generated either a positive value or a negative value. So I already told this thing. So here we are going for the pictorial representation. So L1, L2 are the two coils. So two dots are at the starting. V1 is the applied voltage. I1 is the current flowing in the first coil. M is the mutual inductance between the two coils. So now the current is a starting dot. So the induced EMF generated, so V2 must be a positive value. So how much it is? M di1 by dt. So here it is a open circuited. So secondary is a open circuited. The current value I2 is 0. The current value I2 is 0. So that's why you are not concentrated on I2 current. So similarly, come to the second example. So here, so L1, L2, two coils are there and mutually coupled with a mutual inductance of M. So V1 is the excited voltage. So a current of 5 amperes will flow through the circuit, but the dot conversions. So I1 is entering, but for the secondary side, the dot is leaving dot. So that's why the polarity will be changes. So always remember, polarity changes, the sign will be changes. Magnitude never changes. Magnitude never changes. Okay. So that's why we have to represent the V2 value as minus M di1 by dt. So here also no circuit is connected to form as a closed path. So I2 is open circuited only. So now come to the two more examples. For the V2 voltage is applied in the secondary side. So here coming to the example 3. So V2 is the applied voltage, I2 is the current flowing through the circuit. So L1 and L2 are the two coils. So I2 current is with a ending dot, but the primary current having a starting dot. Anyway, the current in the primary side must be 0 because of open circuit, but there is an induced EMF due to the I2 current. That voltage is V1 is equal to minus M di2 by dt. di2 by dt. Are you understanding? So why you are getting minus sign? The polarities are changed. Due to polarity change, magnitude never changes, sign only changes. So now come to the last example for the same figure, but the dots are, I have taken as ending dots. So here I2 is ending dot. So for the I1 is also ending dot. So under that condition, you can get the positive value of voltage. So what is that voltage value? V1 is equal to M di2 by dt. So V1 is equal to M di2 by dt is common. If the dots are opposite, then you have to go for minus sign. If the dots are same, then you have to go for plus sign. So now coming to the example of two coils are connected in series. So let us assume L1 and L2 are the self-inductance of the coil. So M is the mutual inductance of the coil. So for a series connection, the current must be same. So here the first coil for the current of 5 amperes is starting dot. For the second coil of the same current I of t also starting dot. Then you can say that this is a series aiding connection. So series aiding connection means both inductances are positive. With respect to mutual inductances are also positive. So here the overall self-inductance of the two coils connected in series L is equal to, so two coils are connected in series, L1 plus L2 plus mutual inductance with respect to second current, so M, mutual inductance with respect to first current, another M. So M plus M, how much you can get? 2M. Are you understanding? So first current of the first coil, the mutual inductance is developed with respect to the second coil, that is M. For the second current also, for the second coil with respect to mutual conduction of first current is M only. So M plus M is plus M. So similarly, if you go for the another example, so here the first coil, the current is starting dot. For the second coil, the same current I is ending dot. The self-inductances are L1 and L2 only. L1 and L2 only. the overall inductance can be represented as L1 plus L2 plus minus first coil with respect to mutual inductance of second current is minus M, because the first coil is a starting dot, second coil is a ending dot, that mutual inductance must be negative. So minus M, once again you are getting due to second coil with respect to first current, so that is minus M, finally you can get minus 2M. So overall L is equal to L1 plus L2 minus 2M. So this is, you can call it as series opposing. So aiding the mutual inductance must be taken with respect to two dots either starting or ending. So mutually opposing means the two dots, one is a starting point, another one is a ending point, or second case, one is a ending point and another one is a starting point, that mutual inductance is a negative. So at that time, overall equations you are getting as L is equal to L1 plus L2 plus 2 times of M. Another case is L is equal to L1 plus L2 minus 2 times of M. Are you understanding all of these, students? So this is the concept of mutual coupled circuit.